The next presentation is on effect of reduced graphene oxide depositing on N-Cu2O for solid state photovoltaic cells, authored by KASK Hemachandra and CAN Fernando. Presented by Dr. KASK Hemachandra. He is a research assistant at Nanotechnology Research Laboratory, Wayamba University of Sri Lanka. He has BSc Statistics from Wayamba University, MBA at Cardiff Metropolitan University, UK, and PhD from Wayamba University again. Over to you, Mr. Hemachandra.
Good afternoon, everybody. And this is a present research study that I have been done during my PhD. It's a basic kind of a research that we implemented a solar cell that you are not commercially seen or available that in rooftops. It's a basic research that we have done by developing certain materials. I will be describe the materials. That's the N-Cu2O is the cuprous oxide material. It's a semiconductor. So depending on that, we have previous studies we have done, and I have further developed, and it was to present today. So basically, before on, I want to give an idea what is a solar cell. It's basically, it's like if you get the sunlight and convert into a electricity through a material, a device, it's called as a solar cell. So the conversion process is called the solar energy conversion. That is basic concepts behind a solar cell. So about the history of there are generations of solar cells. In the literature it says 3 generations you can see, the first, second and the third. First is that what you can see available in the industry nowadays, the mono or the polycrystalline silicon cells, solar cells that you can see in the rooftops nowadays. Second, not in our country at the moment, it's a polycrystalline thin film made by cadmium sulfide and etc. Third, that is the industrial revolution belief, and what I have been developed, the kind of solar cell in this third generation solar cells. Example, the QDC quantum dot, then the DSCCS with the dioxide solar cells, polymer solar cells. So in my case, I have developed a solid state, it's named as solid state solar cell. So this is the structure of the solar cell that you can see. It's like a sandwich. If you call a club sandwich, we will have few layers. Same scenario. If you are starting from the bottom, it's the copper. Then the RGO representing in my next few slides as reduced graphene oxide. And the other semiconductor material I am developing is the cuprous oxide. And finally, the ITO means the conductive glass plate to seal as a solar cell. So this is the basic schematic structure of the solar cell. So I will describe how I have been developed this solar cell step by step. Before moving on to that, I want to give a brief idea because I think you are a little bit not familiar with the materials. So a cuprous oxide, we call it a reddish brown color, and it's have a band gap of 2.1 electron volts. That means it confirms that we can use it as a semiconductor material. Normally they are all P-type, N-type that we are calling semiconductors. Both can be developed through this cuprous oxide. So that is the main key that we have developed this solar cell. So there are advantages. It's low cost, non-toxic. Fabrication process is very simple. That what we have developed in our laboratory, and it have been used in electronic devices such as in my study it's about the solar cell. Then we are nowadays dealing with the sensors and other electronic stuff. So on the next thing, this is the next biggest thing that we are the western part of the country is dealing with. It's called the graphene. If you take a bulk graphite and equal into the number of bulk sheet, if you can remove one sheet, we can call it as a graphene. There is so many advantages over graphene. So if you take 1 to 5 sheets of graphene, it's like 97 transparent and it's high conductivity. It's the base of the graphite, charcoal, carbon nanotubes, all the structures, the base is the graphene. So it is found in 2004, and it is the strongest and the thinnest material that ever found at the moment. So through that, we are developing the graphene oxide. It's containing with its lattice structure, honeycomb structure that you can see in the bottom of the picture. The black dots represent the carbon atoms, but with incorporating of the oxygen molecules, we can develop, we are calling as the graphene oxide. So through that, through synthesis the graphene oxide, there are popular 4 techniques. In my technique, I'm using the Hammers method. With the modification, we can modify the oxygen and carbon ratio to develop our graphene oxide. So we are using the modified Hammers technique. I will give a brief idea of how to fabricate the graphene oxide we done in our laboratory. It's like take a powdered graphite and mix with concentrated sulfuric and sodium nitrate in an ice bath, because it's a high temperature. In a seconds, the temperature goes more than 100. So we have to be very safety. We have to drag into an ice bath, and when you are adding those things with potassium permanganate, and we have to vigorously stir for 30 minutes. Then the powder becomes a suspension after 30 minutes. It's becoming like a paste. I don't know if the picture is clear. You can see the bottom, the brownish color paste will be formed. After that, it's a base. Then we are adding distilled water, and to remove the ions and residues, you're using hydrogen peroxide. So the brown color paste becoming yellow color. So after that, after centrifuging and treating with the HCl, we can remove the residual ions, and drying we can get the graphene oxide powder. That is the base of it. So applications not in the industrial level, but it's a huge impact. We can use in electronic devices. Think about if it's transparent and high conductivity, we can use it in as shown in the bigger figure. The unflexible devices, we can develop the ICs, transistors, those stuff we can develop. So other than that, the filtration, photovoltaics that I'm dealing with, and energy storage, there are a lot of researches carrying on. Those are the materials on this, and through those materials, these are the basic 3 steps I'm going to describe how does we have developed the solar cell in our laboratory. In the first initial steps, there are so many synthesis. We are calling synthesis depositing some other material. In our lab, we have deposited the graphene oxide as reduced graphene oxide by using the electrophotic, its naming as technical term is EPD technique, to deposit graphene oxide on a well-cleaned copper sheet. We take a piece of copper, high purity, and we will mechanically polish like a mirror surface. And as shown in the right side of the figure, you can give the electric power with the platinum plate as a counter electrode, and in a graphene oxide solution. And if you give the time, we can deposit the reduced graphene oxide. Even though I'm saying it, I'm going to prove it later on that we have successfully formed that graphene oxide on top of the copper. Thereafter, depositing the cuprous oxide. In our previous studies, we have some patents as well as some high impact journal publications how to fabricate cuprous oxide on top of the copper. Same scenario we applied, that is after depositing the reduced graphene oxide, this RGO represent the reduced graphene oxide immersed in a copper sulfate solution, and if you boiled it, we may have a layer of cuprous oxide. Again, I'm saying I will show that the formation have been done. Varying the boiling time, we can vary the thickness of the cuprous oxide. So finally, to make it a complete circuit, the ITOM is a conductive glass plate. In the bottom side of the glass plate, it's conducting to make it sealed. And if you connect and if you check with the ammeter, irradiate into the sunlight, we generate electricity. Small scale milliamperes, but it's generating. So these are the publications that we have done so far based on the cuprous oxide. So we have further developed The introducing part is the RGO, that is a reduced graphene oxide in between the copper and the cuprous oxide, because previous studies we have developed copper and the cuprous oxide, but we have introduced a new layer of reduced graphene oxide and enhance our photocurrent. So the mechanism, like behind it, like in here, if you take the bottom, like I said, when I'm boiling the thing, we can change the thickness of the cuprous oxide. So if you have lesser time, the cuprous oxide not exceeding the thick layer of the graphene, so it decreases, we are saying decreases the photocurrent. So boiling more time and we get a high thickness means we get the thing. And these are called the scanning electron microscope images, that is scanning like a microscope with a high power. It's confirmed the left hand side, the well clean copper plate image, and deposited, you can see the cloudiness in the right hand figure. It's have the reduced graphene. Confirmed with the bottom graph, it's called the EDAX. Carbon element is represented in there. These four figures that is representing, you can see a little bit stones or crystalline, we are saying that is a formation of cuprous oxide. So this is the FTIR or Fourier transformation, another confirmation of the graphene oxide have been synthesis. If you have synthesis something, the bonds will be represented from this spectrum. We can confirm with the literature. And another one is the XRD, X-ray diffraction. It's again confirming the molecules that we have been developed. Starting from the bottom is the graphene oxide, then the cuprous oxide, and with the formation of the reduced graphene oxide with the cuprous oxide, you can see the top. So it's successfully shown the cuprous oxide and the carbon represented in our sample. So this is the another one of the diffuse we are calling that we are using in our laboratory to confirm the graphene oxide have been synthesized properly. With the literature, it's confirmed with the peaks that you will see in these two. It's confirming that the graphene oxide have been developed. Same scenario in here. When you are proving it's a semiconductor device, these graphs, we say this edge, we will say the cuprous oxide edge. It's confirmed like 1.9 electron volts. Same after depositing the cuprous, depositing RGO, the same sample we analyze, but you can see the shape is similar. That means there is no effect, so there is no transformation done. This is the output, the voltages and the currents. You can see clearly it has enhanced. The conversion is 0.4 to 1.4%. So through that, this is the conclusions. It was done for the first time. Enhancement done, checking with our previous studies. In here, the reduced graphene oxide, there's a mechanism and remarkable stability have been observed. So these are the references, and I have to acknowledge the NRC providing the instruments and the grants, and our research laboratory, nanotechnology research laboratory in Vayamba University of Sri Lanka. Thank you.
Thank you very much, Dr. Hemachandra. Let us invite few questions on the interesting presentation.
Thank you for your presentation. Can you say something about your power conversion efficiency of your devices and how useful that power conversion efficiency is compared to other devices for solar conversion?
Like the moment, that's where, like says in our, at the moment it's like 1.4% conversion efficiency, but if you go for silicon, it's practically implemented more than 20%. But we have further enhanced same cell up to 3.8%. But the thing is, when you're comparing with the cost analysis is done, it's more like the cost is low because materials are low, and when you compare, even it's though we have the less amount of the power conversion efficiency, when you're comparing the cost, still we have to deal with the industrial level. It's true, but as a basic research level, we are up to a certain level.
So I think very importantly you made the comment cost then. So what sort of size are you making your solar cells, and when you start making it larger, do you think there's going to be a problem with scale up?
So can I?
So at the moment, how large are your solar cells that you're making 1.4% power conversion
Yeah,
efficiency?
it's like a 1.3 centimeter. It's very tiny thing. 1.3 centimeter cell. It's like a thumb size one.
So once you start scaling it up, it does take a lot of effort, and therefore it's not very easy to scale up any of these products. So you have to be very careful when you're using new materials. I think like in the previous question that was put, do a proper cost analysis. Just because you have materials that are giving you new results doesn't mean that you will be able to get huge cost benefits later on. So you have to always look at what the current technology that is there and how do you displace that using something else that could be more efficient and cheaper at the long term. Thank you.
Thank you.
Can I add something to that question? In addition to the cost, I see another advantage in this technology because we can commercialize the production locally, because the other production is to be imported right now. Introducing production in the country is not really straightforward. Can you comment on that? Can we introduce production locally, this technology?
Still it's a basic research level, but we have like good institute. We have the Nanotechnology Institute at the moment, and there are local universities developing with the nanotech at the moment. So commercially, thing is, it's like we can gain it. Syntech is about to do some serious commercially aspect of giving value added, but as I said, the graphene, we have the graphite highest purity among